Good morning, everyone. Very happy to be here and see all of you. My name is Michal Feldman, and together with Brendan Lucier, we are organizing the workshop on a very important topic, optimizing the effort of others. Up until recently, so this is part of algorithmic game theory, which is the intersection of algorithms and incentives. And up until recently, AGT, algorithmic game theory, focused mainly on algorithmic mechanism design, but now there are so many other frontiers in the intersection of algorithms and incentives, and one very important one is how to optimize the effort of others. And when Brendan and I started to organize this workshop, we noticed that there are many new lines of research that have been mainly separated up until now, including algorithmic contract design, delegation, strategic classification, scoring rules, that share many commonalities. And we hope that this workshop will bring together the researchers that have recently done beautiful research on all these areas and would open up interesting discussions that would lead to nice follow-up work and identifying additional commonalities. So very happy to be here. Thank you, Brendan. It was a pleasure organizing this with you. And today we will have two tutorials. The first tutorial is by Inbal Talgam Cohen from Technion, Israel, and Paul Duetting from Google Zurich. So I'm happy to introduce Inbal, who will do the first part of the tutorial. Thank you very much for coming, and hope you enjoy the workshop.
Yeah, thanks so much. We'll start in a minute once the presentation is working. Okay, can you hear me well? Okay, so thanks everybody for coming. I will be presenting the first part of the tutorial. I'll present the model and then talk about contract design under uncertainty. Then we'll have a 5-minute break, and Paul will talk about approximation and complexity issues. So a bit of an introduction and motivation. As you all know, algorithms have an increasing effect on economics and society. So they determine what resources we get through auctions and so on, what content we see through recommendation systems and regulation systems, what opportunities we face. So will I be eligible for a loan, for example? And finally, what we work on and what we put our effort into through, for example, online labor markets. And I'll be focusing mostly on the last two aspects. So as algorithms are influencing people more and more, they have to take into account the fact that they're interacting and influencing strategic players. By strategic players, I mean players who are acting to maximize their own utilities, okay? Acting in their own self-interest rather than the goals of the algorithm. So any algorithmic design has to take this into account if it wants to succeed. What I've said up till now is that there's an interesting intersection between algorithm design and incentives design, so computer science, theory, AI on one hand, and economics, game theory on the other hand. And as Michal mentioned in the introduction, an area which has been very well studied in this intersection is algorithmic mechanism design. And we have 2 decades of very fruitful work on this. But there are other areas within this intersection. Namely, there's algorithmic information design and algorithmic contract design, which are emerging in recent years as very promising areas of research. I will be focusing on algorithmic contract design. I did want to point out that in economics, all of these are almost equally important, I would say. Not algorithmic, just contract design, contract theory, and mechanism design, the theory of mechanisms. Both of these have been recognized by the Nobel Prize. Okay, so this is going to be our focus. So what is a contract? A contract is just an economic tool which aims to incentivize a strategic player to put in effort for somebody else. So somebody else is going to enjoy the fruits of the effort of a strategic player. So of course, if we want a strategic player to put in effort for us, effort is something that is costly, we have to pay them. And pay here is, in between the quote unquote, because we don't necessarily pay with money. Okay, so a couple of examples. If we're outsourcing a task to a freelancer, we will pay the freelancer and we will enjoy the fruits of their work. If we're trying to get students to learn, we have to motivate them somehow. We're not going to pay them, obviously. We use grading to incentivize them. And contracts are basically everywhere. This quote is from the press release of the Nobel Prize I was mentioning. Modern economies are held together by innumerable contracts. So let me give you a concrete example so we have something in our mind throughout this tutorial. Here's a very simple contractual setting. During the workshop, we'll kind of make it more and more general, but just the basic setting, just two players, a marketing agent in this example who's hired by a principal, the website owner, and the task is to promote the website. Okay, get more traffic to the website, maybe increase the website in the search engine's ranking. The agent will have to take action in order to get traffic to the website. And the principal will enjoy this, and the principal will pay the agent. Okay, that's the whole example. And I want to point out at this early stage two defining features of this economic relation. So the first is that the agent's action is not directly observable by the principal. This is sometimes known as moral hazard or hidden action. And what do I mean by this? So if you're hiring somebody or delegating a task to somebody, you're not going to closely watch over their shoulder and see exactly every action they take. You don't know what effort they put in. You can think of students that you're teaching a course to. You don't know exactly how much effort they put into your grad students. You don't exactly know how much time they spend on a problem. Okay, so this is the first feature. You want to get somebody to put in effort for you, but the contract can't look like something like, okay, if you work, you put in effort, I pay you, because you don't observe directly the effort. Second feature is something called limited liability, which is just a fancy name for the fact that only the principal pays the agent and not vice versa. Okay, the agent is sort of the party who has less deep pockets. They're not going to take money out of pocket and transfer it to the principal. This is very natural. I mean, when you hire a freelancer, you're the one who pays them and not vice versa. Okay. What's happening with contracts? What we saw on the previous slide is an example of just a classic contract. And what's happening is very similar to auctions. Contracts are growing in scale and complexity, and they're moving online, and they're becoming more data-driven. And if we think of our examples, there are these online freelancing platforms, which are very large and dynamic and so on. You can think of massive online courses. And this motivates an algorithmic approach. It could be useful and timely to apply an algorithmic approach. This has already been kind of, there's kind of proofs of concept of this in early pioneering papers by Michal and by others. What I want to show you is what's been going on in recent years. This has kind of picked up speed, and there's starting to be a lot of work on this. So I said an algorithmic approach to contracts. Here's what I mean by this. This is the way I see it. So I think either if a mechanism or if a contract is just a type of algorithm which has an input and an output. The mechanism's output is usually about resource allocation. Okay, so who gets what and for how much. A contract output is going to be similar, but about efforts. So who does what and for how much. You can think of it as a kind of mechanism for allocating efforts. And what makes this interesting, or what makes this a sub-area of algorithmic game theory, is the interaction with strategic players. So for a mechanism, the input is reported by strategic players, and for a contract, the effort is carried out by a strategic player. Your algorithm computes some solution, but it's only kind of a recommendation to the strategic agent. The strategic agent has to choose to put in the effort to carry out the output of the algorithm. So both of these are optimization problems. You're maximizing some objective, maybe welfare, maybe revenue. We'll be focusing on revenue. And the optimization problem is subject to incentive constraints. In mechanism design, you're trying to incentivize truthfulness. And in contract design, you're trying to incentivize effort. OK. So that was kind of the introduction and the motivation. And I'll now kind of tell you an overview of the results I hope to show you. We'll see how much time we have. So I want to focus on contract design under uncertainty, because this is one of the areas where we think that an algorithmic approach can be very fruitful. So what do I mean by uncertainty? Well, you're contracting with an agent, and you may not know everything about the agent. Okay? This is very typical of internet online settings. In particular, the agent is taking action for you. You might not know how effective this action is going to be or how costly it is for the agent to take. And the approaches of algorithmic design and economic design to uncertainty kind of range on this axis from average case optimality on one hand and worst case optimality on the other hand. I think average case is more typical of economics. Worst case is typical of computer science. If you're kind of familiar with revenue maximization, worst case is a bit too optimistic. We can't really do that. So I'll show you two approaches. One of them is on the average case side. It's called the Bayesian approach. And this is what the approach that's taken in works like Tsai et al. About mechanism design, if you're familiar. Algorithmic mechanism design, if you're familiar with this. I'll actually start with an approach that's in between average case and worst case, similar to semi-random models that you may know from TCS, where there's kind of a mix between average case, something distributional, and something that's worst case. OK, so here's an overview of the results. For robustness, I'll show that a subclass of contracts, very simple subclass called linear contracts, are robustly optimal, max-min optimal with respect to distributional details. This is based on joint work with Paul and Tim Roughgard and related to some very interesting research I'm listing on the slide in case you're interested in looking more into. For the Bayesian approach, I'll introduce an emerging area of research on optimal contracts with types. Is there a Marshall-like theory? Can we get simple, approximately optimal contracts? This is based on joint work with Paul, Talalon, Ying-Kai Li, and related to also some very nice literature, including by Brendan and others. OK, so let's dive into the model. What I'm showing you now is the classic model of contracts. It's by Holmstrom, one of the Nobel Prize winners, as I mentioned before. I do have slight change from the standard model, but I think for this audience, there are no economists here. It won't really matter to you, and you can ask me if you want in the break. So what's the model? The agent has n actions or n effort levels that they can choose from. If you take effort, you're going to pay a cost, and the costs are increasing with the effort level. The principal can get one of m rewards from the efforts of the agent. So what the mental picture you should have in mind, and I'll show you on a slide in a few minutes is kind of a matrix with n different effort levels, m possible rewards from these effort levels. And what maps an effort level to a reward? Well, that's a distribution. Okay, so the agent will take effort, but high effort won't necessarily lead to high reward, and vice versa, because things are noisy. Okay, this is the way it happens in real life. Maybe you have a student who's not working that hard, but still manages to do well on the exam. Okay, or you have a grad student working very hard, but stuck on a problem because it's just, it's just hard. So the way this is modeled, every action has a distribution. I'm going to denote it by capital Fi for action I. The distribution is over the rewards. Fij is just the probability that action AI yields reward Rj. And very useful notation, capital Ri. This is just the expected reward. Okay, so I have a distribution over the rewards. This is just the expected reward associated with action I. So to summarize the setting, we have vector of costs associated with the actions. We have the rewards, the vector of rewards. The parameters of the model are n and m, okay, the dimensions of these vectors. And we have the matrix of distributions. That's the model. Now, I didn't tell you what a contract is. So what's a contract? A contract for every possible reward Rj will specify a payment, a transfer from the principal to the agent. Okay, so transfer Tj. And as we said before, there are two defining features, and they really kind of very clearly show up in this model. So for a reward, first of all, the easy thing to see is that the transfers are non-negative. And this is exactly the limited liability that I mentioned before. Okay, only the principal pays the agent. And the second thing is, look at what the transfers depend on. They depend on what the reward is, not on what the action is, not on the effort level. Okay, because the effort level, as we said, is unobservable. The principal only kind of sees the bottom line, the results, the rewards that the agent gets to them. Okay, we already mentioned the notation of capital Ri. This is the expected reward. Just like that, we have also expected transfer. Okay, that is if the agent takes action AI, according to the contract, what is the expected payment from principal to agent for this action? So now we have everything we need to analyze incentives. Okay, so the agent will choose an action that maximizes her expected utility, her expected payment minus her cost. The principal, if the principal gets the agent to take action AI, she gets the expected reward from this action minus whatever she has to pay, okay? So that's capital Ri minus Ti. And here's a nice way to think of what's going on here in the economic sense. So you can think of every action as inducing a welfare pie, okay? The expected reward from this action minus what you need to pay in terms of cost to get this pie. And the contract, what it's doing is really it's dividing the pie. Okay, so it's deciding how much of the pie will go as utility to the agent and how much of it will go as revenue to the principal. So it's kind of whatever action the agent chooses to take, you get bigger or smaller pie, and the contract divides the pie. Good. To summarize the setting, here's how it works in terms of timing. At the beginning, everybody knows the setting, everybody knows the costs, the rewards, and the distributions. The principal designs a contract. The agent looks at the contract and decides which action is maximizing their utility and takes that action and pays a cost that is associated with the action. The cost is also associated with a distribution, and the reward is drawn from this distribution, Rj, okay? And then, according to the contract, if you have reward Rj, the principal pays the agent Tj. And we're looking at this whole interaction from the point of view of the principal, who is trying to maximize their own revenue. Okay, so we'll say a contract is optimal if it maximizes the principal's expected revenue. Good. I want to say, at this early stage, now that we know the model and we know what the optimization problem is, it's an easy problem computationally. Okay. So here's what I mean. So think of the problem of designing the optimal contract, the revenue maximizing contract. Now think of an even simpler problem, the min pay problem, where the input is the setting and some action, and the output is what's the minimum expected payment that needs to be transferred from the principal to the agent to incentivize the agent to take this action that's given as part of the input. This problem is easy, okay? It's solvable by writing down a linear program. And if you want to solve the more complicated problem of optimizing the contract, you can just solve n such min-pay problems, one for each action, find out for each action how much you need to pay the agent to get them to take the action, go over all the actions and compute, just calculate what's going to be your revenue if you incentivize that action, and that's it. Okay, so why aren't we satisfied? What's still to research here? So this approach has two downsides. First of all, it requires perfectly knowing the distributions and the costs, so perfectly knowing something about your agent. And then the resulting contract can be weird. Okay, I'm going to show you an example of what I mean by weird in a couple slides. Good, so that was the whole model. I'm going to show now a couple of examples. The first example will be very simple. So here's that matrix that I asked you to kind of imagine before. Here it is on the slide. This is a very simple setting. We have two actions, two rows. We have two rewards, two columns. And you can see the distributions on the rows. And this is why I say it's a super simple example. These distributions are just point mass distributions. So it makes everything very easy. I've shown the expected rewards on the right, okay, capital R I's. And we can analyze the setting. If you want to incentivize the agent to stay in bed, an action that has cost 0 for them, you don't have to pay them anything. No matter which reward they get, the low or the high reward, just pay them 0. They will stay in bed, and your expected revenue will be 1, which is the expected reward. If you want to incentivize them to take action that is more effortly, then you have to pay them at least 4 over 3, which is their cost. It turns out that in this case, you can pay exactly 4 over 3 by this contract, okay, this vector of payments, transfers, and your expected revenue will be 3 minus what you pay, which is 5 over 3. So that's a very simple example. Things become more complex when you take n and m to be larger than 2. Okay, the binary case, either of the binary rows or binary columns is more simple, and this Paul will talk about more. I'm not going to analyze this example. I just want to point out one thing. If you compute here the optimal contract, this is what you get, and this is weird. Okay, this is what I meant by weird. Here's what I and others find weird about this. Look at this part, and you can notice that the agent gets more and more reward for the principal, and still the principal pays them. This is the agent getting more and more reward for the principal, and this is what the principal pays the agent. And you can see the agent is not being paid monotonically. Okay, the payments are actually decreasing even though the principal is getting more reward. So this is really weird. It's not what contracts look like in practice. And this is one of the downsides of just taking something that pops out of the linear program and using it. Okay, I had a third example. I'm actually going to skip this. I wanted to show the connection of contracts to classifiers. I think Hara will be talking about this after our first tutorial, so let me skip it. Okay, so contract design under uncertainty. I'm starting with a robust approach. So this is more modern work. Until now, we saw kind of classic model, and now I'm switching gears and looking at recent work. The recent work is addressing actually a classic problem as well. So what is this problem? Why are the contracts that we see in practice clearly suboptimal? Okay, they're not that thing that pops out of the linear program, even though it's simple to compute. Okay, what's the reason for this? Sorry. And this is, of course, this puzzle has been noticed by economists, and Holmstrom and Milgrom put it very nicely. They particularly look at a subclass of simple contracts that's called linear. And this is going to be very central to everything I have to say till the end of this part of the tutorial. So let me tell you what linear contracts are. Luckily, it's really simple. So a contract is linear if it's just determined by a single parameter alpha, which is between 0 and 1. And this contract is saying something like this. The principal tells the agent, if you get me reward of rj, I will pay you alpha rj. Okay, so if alpha is half, the principal is telling the agent, I give you half of whatever reward that you get from me. Okay, very, very natural contract. And it's kind of intuitively clear that this is going to somehow align the incentives between the principal and the agent, but it's suboptimal. Okay, we saw the complex example. It's not optimal. It can be very far from optimal in certain settings. Okay, so economists have also looked at this question of why linear contracts are popular in practice and given explanations based on robustness. And I want to give you a new explanation that we found. Our explanation is based on built-in robustness of linear contracts towards distributional details. Here's what I mean by that. So we have our matrix of distributions, and we have the expected rewards. Each of the rows has an expectation. What I want you to notice is that the way a linear contract operates and the incentives that it creates and the revenue that it gets, all of that is only depending on alpha, the parameter, and on the expectations. Okay, the details of the distributions don't matter at all. Okay, and here it is in this welfare pie image. So I have the welfare pie, and the part that goes as the revenue to the principal and the part that goes as an expected utility to the agent and determine all of the incentives, both of these only depend on the expected reward and the alpha. Okay, there's no capital TI here. The probabilities, they never come into play. Okay, and I want to translate this into a theorem about optimality in the maximum sense of linear contracts. So here's a theorem. Consider a contract setting with uncertain distributions. I'm going to show you this in a minute. With uncertain distributions and known expectations. Okay, these are the given expectations. The linear contract will maximize the expected revenue in the worst case sense, meaning that when the distributions compatible with the given expectations are chosen in worst case, linear contract is going to be optimal. Okay, the takeaway from this theorem, if you're in doubt about something in the setting, in this case, you don't know the details of the distributions, only in their expectations, take designs that are agnostic to the unknown details. Take, for example, in this case, a linear contract, which it doesn't matter at all what the details are. It's going to operate in the same way. Okay, so here's what I mean to make the theorem a little bit more formal. Here's what I mean when I say setting with uncertain distributions. The expectations are set in stone. Okay, we know the costs, we know the rewards. What we don't know are the details, the actual probabilities. Okay, and when I say compatible distributions, what I mean is choosing these numbers such that if you compute the expectation of every one of the rows, you get these capital RIs, which are set in stone. You get the given expectation. And when I say worst case over compatible distributions, I mean that these numbers are chosen by an adversary. Okay, so now I can state the theorem more formally. We're given the expectations, okay? And let's take calligraphic F to be all the distribution matrices which are compatible with the given expectations. And then a linear contract is maximum optimal, meaning that the expected revenue that it gets is the maximum over all contracts of the expected revenue, where the expectation is taken over distribution matrix, which is worst case over all the possible compatible matrices. Okay, so you can see here, as I said, this is kind of like semi-random. Okay, you have the part that's in expectation, that's using randomness, that's using a distribution, but the distribution is chosen worst case. Okay, so very quickly, what's the proof idea? Just to kind of get a feel of how one can show this kind of result. Let's fix the expectations, and the result is through a key lemma that says that for every contract that's nonlinear, I can show you compatible distributions, compatible distribution matrix F, and a linear contract, such that the expected revenue of the linear contract over this compatible distribution matrix is at least that of the given contract that I started out with. Here's a visualization of that key lemma. The matrix I'm showing here is not the matrix of distributions in the contract setting. Rather, it's a matrix of a zero-sum game in which the contract designer is the row player and is choosing the contract. And the column player is this adversary, the kind of demon figure that I showed before, okay, choosing the worst-case compatible distributions. If I look at a contract, a strategy of the designer, and a compatible distribution, a strategy of this adversary, then I get expected revenue, which the designer is trying to maximize and the adversary is trying to minimize. So just a classic zero-sum game. And the lemma is saying the following. If we look at a contract that's nonlinear, okay, give me such a contract, I will give you back a compatible matrix of distributions and a different linear contract. And the expected revenue of the linear contract on this compatible distribution matrix will be better than that of the contract that I started out with that was possibly nonlinear. The distance between this key lemma and the actual theorem is not far. All you have to do is remember the inherent robustness of linear contracts. The way this robustness will look like on this slide basically is noticing that in this matrix of the zero-sum game, it doesn't matter which compatible distribution matrix the adversary chooses. The linear contract is agnostic to that. Whatever choice the adversary makes, the linear contract makes the same expected revenue. Okay, so if you try to see what is the maximum strategy for the contract designer, it's a linear contract. And that's basically the whole proof. Good. Sorry, that's the whole proof up to the key lemma, which I won't go into. Stay at a high level because this is a tutorial. Okay, I want to spend the last 5 minutes of this part of the tutorial talking about the second approach to uncertainty, the Bayesian approach. We have a talk in this workshop that's going to go into that in more detail. John's talk, I don't remember if that's tomorrow or the next day, but here's kind of an introduction to that. So let's return to our example of internet marketing. Where, remember, we have an agent that was hired by a website owner to promote a website. And here's a very natural twist or addition that you can make to this example. Well, you have uncertainty about the agent. You don't know exactly who you're hiring. Think of the internet or something. You can model this as the agent having a type that's privately known to the agent and not known to the contract designer. So the agent can be a very strong worker or maybe a poor worker. And you don't know, as the contract designer, and the question is, how is this going to affect the contract design? I'm going to assume a Bayesian assumption that the distribution of agent types in the population is something that I know. Hopefully, going forward, as this area of research evolves, we can replace this by some learning methods, learning the population instead of assuming that it's somehow known. Okay, so if we kind of return to this picture of what's a contract, basically, or what's a contract and a mechanism from an algorithmic point of view, I'm basically merging the two together. Once I add types, I'm kind of merging the two together. We can call this model contract with types. And the input is a type reported by the agent. And the output is just like a standard contract, what action to take and what is going to be paid. And again, like a standard contract, you have to incentivize the agent to take the action. The agent is the one choosing the action, and you want to provide them the incentives to choose what you want them to do. Okay? The design goal here is, again, optimization problem. You want to maximize the revenue, but you're subject to multi-dimensional incentive constraints. You need to incentivize both truthfulness and the agent to put in effort. Okay, so it sounds hard, and let me show you what we know about this. I just want to mention that this contract with types title, I could just as well give it the title of mechanisms with effort. Okay, it's dual view of the same thing. So the research agenda is to see if key algorithmic mechanism design results generalize when we look at mechanisms with effort or contracts with types. And I don't have much time. I'm going to show you very briefly what we started to do. We started to look at two not classic, or by now they're kind of fundamental classic results in mechanism design and in algorithmic mechanism design. The first one is Meyerson's theory of revenue optimization, and the second one is simple, approximately optimal mechanisms. Both of them are kind of fundamental results, which would be very nice to have in this new model. So I have two slides quickly giving an overview of the model and results, and then I'll summarize. What did we do? The first key step was to formulate a model in which the type is single-dimensional. Why is this important? Because Meyerson's theory, it only applies to single-dimensional types. So this is the first step that we had to do if we want to hope to do anything that's Meyerson-like. Okay? And the way we did this is that the agent's type C is just one number representing her cost per unit of effort. Okay, and this number comes from some distribution. This is the Bayesian assumption that I know the distribution. Here's the way it looks like. The setting is very similar to what I had before. You know the rewards, you know the distributions. But what you don't know is what the costs of the actions are. You do know how many units of effort each action requires. But to get the costs, you need to multiply the number of units of effort by the cost of the agent per unit, so by the agent's type. Okay, so this is the model. And under this model, we showed approximate optimality of linear contracts in the following sense. If we have the type, the single-dimensional type from the model on the previous slide, and it's coming from a distribution G, okay, distribution G that's very different than the distribution of the contract matrix. Okay, this is now the distribution of types. Well, if it's a uniform distribution, a linear contract turns out to be optimal. And if it's MHR with some twist, technical twist that I won't go into, but please ask me in the break. For example, if it's exponential, then linear contracts are constant factor approximation and factor 2 approximation. This is proved by a Meyerson-like characterization of implementability, and we were quite surprised by this because of the multi-dimensional nature of the incentive constraints. Okay, they're unknown type and unknown effort. Okay, they're two dimensions, and indeed we can show that a lot of the complexities of multi-dimensional mechanism design pop up, but still very kind of a bit surprising positive result. To sum up, we showed a classic model, and we went over a classic model in economics. We discussed how the algorithmic lens can be helpful if you're trying to deal with uncertainty in this model, and we saw the key role that simple designs play. In particular, we focused on linear contracts. We showed they're optimally robust, and we showed they're approximately optimal when agents have types. There are a ton of open problems. Please ask us after the tutorial or in the break. For example, learning and agent population and so on. And let's now take a break. And Paul will, in 5 minutes, talk about approximation and complexity.
Thank you very much, Inbal. Maybe you can stay there for a quick couple of questions, if there are any. Yes, Yanis.
So is the principle considered honest?
I would say yes, exactly like in auction design, you kind of think of the principal as the one having the commitment power, and I guess as as this theory progresses, we can see relaxations like we have in auction design, credibility and so on.
Jason.
Yeah, so many times when we look at robust analysis, we look at a ratio to the optimal that knew the thing that you don't know. And you've looked at a more absolute analysis. Do you have anything to say about ratio analysis and why that's maybe not good here, or what's your philosophy there?
So I think that the ratio is something we looked at in the model with types, and there we were able to kind of find the right conditions under which we can get a good ratio. In the model without types, we looked at this, and you can show examples where a linear contract is far from being approximately optimal, which was surprising to us. I mean, so I'm still, I kind of showed a bit of ongoing work. I'm still trying to kind of settle these two things in my mind. But yeah, I think there's a complex story there, yes.
Great. One more question. Brendan.
Great, thanks for the wonderful tutorial. I find myself thinking about things like Mechanical Turk or something like this, where I'm like contracting with the same agent many, many times.
Yes.
I guess I'm wondering if I'm modeling that, are there certain constraints that should naturally be relaxed? Are things become easier there? Or does it reduce down a similar problem?
Yeah, I think it's a great question. I haven't looked at this myself. One of the pioneering works I showed was by Jen Wortman-Vagan and others, and they really, their motivation was Mechanical Turk, and they looked a little bit at these kinds of questions. If you have a repeating setting, then it's natural to involve learning, and that's what they start to do. But I think there's a lot more to do based on that, pioneering work.
Okay. Let's thank Inbal again for the great talk. Paul, do you need a few minutes break, or would you like to start?
I mean, as you prefer.
Okay. Good. So our next tutorial giver is Paul Duetting, who will give the second part of the first tutorial. Thanks, Paul.
Yeah, but now we are seeing it. Because you have notes.
No, it's okay without.
You sure?
Yeah.
I'm sorry.
Yes. I can also present it the other way.
Okay, let me check. Not for them. Let me check.
All right, welcome back. I hope you can hear me all right. Perfect. Yeah, so welcome to the second half of the tutorial on algorithmic contract theory. As Inbal said, in this second part, I want to focus on complexity and approximation, and hopefully can convey this idea that contract theory, just as mechanism design and other fields in AGT, have this very nice and intimate connection to combinatorial optimization problems, which I hope are interesting to this audience. So the general motivation here is that this complexity and approximation approach was and still is very successful in the wider realm of algorithmic game theory. I'm thinking of results such as the PPID completeness of mixed Nash equilibria, or for example, combinatorial auctions, where TCS research has shown that gross substitutes sort of act as the frontier of tractability for welfare maximization, and they're very nice and still ongoing work on kind of finding good approximation algorithms for valuations that exhibit some diminishing returns. So for example, for submodular valuations. And more generally, I think this computational lens of approximation and complexity has very nice things that it can contribute. And in particular, I'm thinking of the following. So for one, I mean, that's maybe the most obvious thing. It delineates somehow tractable from intractable. But what I think is maybe even more important are the other 2 points. So first, that it often reveals some structure intrinsic in the problem. That's very nice and maybe sometimes only visible through the computational perspective. And you will see some examples of this today. And then I think more generally, so why do we do this theory research? Maybe in the end, we want to identify, at least theoretically, aspects or insights that help inform the design of maybe simple practical algorithms that we can use for real-life problems. So here in this case, this would of course mean simple contracts. Okay, so if we go back to this example that Inbal mentioned in the first half, or the model of Holmström and Grossman-Hart, so this principal agent model, and our running example of a website owner that tries to hire a marketing agent. And if you think about this problem, and maybe also the presentation in the first half, then maybe you think, oh, that's really a very simple, or maybe oversimplified model, right? And in practice, maybe this problem has much more structure that we could use and exploit. So for example, in this very concrete example where the website owner is trying to hire a marketing agent, outcomes could be very rich, right? So there could be different types of visitors that can be attracted to a site. There could be different numbers of each type that are attracted, and the website owner may have different preferences over these, and somehow we could try to use this and exploit this computationally, right? And if you kind of switch roles and think about the marketing agent, so the expert here in this case, then also for her, maybe setting up such a campaign is not just taking an action, right? It's often something that's more complex, right? So she can do several things. She can set up a campaign here. She can, right? So she will do something. And maybe the more she does, I mean, this will have diminishing returns. And the question is kind of what's kind of the right point she should hit to maximize kind of her long-term success in the field, maybe. Okay, and indeed, there's some emergent literature which takes this complexity and approximation approach, which was very successfully applied in algorithmic mechanism design, and applies this to contracts. So I've splitted this up here into earlier work, which happened around 2005-06. So Inbal already mentioned this very nice paper by Babayov, Feldman, and Nissan on combinatorial agency. And there's also some recent work to which I've contributed, and which I will cover in part also in this talk. Okay, and plan for the second half will be that I want to talk about this recent emergent work on combinatorial contracts, highlight connections to combinatorial optimization problems, and how it kind of puts a spotlight on structure, which is maybe otherwise not visible. And I thought kind of didactically, it could be useful to structure the talk along the different dimensions in which you could make the base problem combinatorial, right? So think of my example, right? So for example, the outcome space could be richer. How can we exploit this to speed up computation? Or maybe the agent takes a set of actions, maybe with diminishing returns. How would we design contracts in that setting? Or ultimately, maybe the agent is really like a marketing agency. So there are a couple of employees who can take action and put in different effort levels. How do you incentivize such a team to achieve the outcomes? And I should say that most of this is really like very early work. I think it's showing promise, but there are also many open problems. So hopefully you can take away one or two problems that you think you could solve yourself. All right, so let me begin with the first direction. So that's combinatorial contracts with many outcomes. Okay, and the model that I want to describe here, what's kind of our first endeavor in this direction. So it's taken from a paper that I've written with Tim Roughgarden and Inbal, Talgam, Cohen. So in all of the approaches that I will show you, I will keep some aspects of the problem simple, but make one aspect combinatorial, so to really pinpoint how this affects the situation. So in this case here, I will stick with the assumption that there's a single principal that interacts with a single agent, and also the agent just takes actions. So there will be n actions, A from some set A, and as before, they have some cost. So taking an action is costly. In and by itself, the agent doesn't want to do anything. Okay, so then how do we model now richer outcome spaces? And I'm proposing this high-level approach, which I will then instantiate to something very concrete, right? So we'll generally have a succinctly described but exponentially sized outcome space. As before, an action will trigger a distribution over outcomes, and for computational purposes, I want that this has some succinct polynomial representation, this distribution. And in addition, I have a reward function that takes my realized outcome and maps it to a reward, a non-negative real. Okay, and this should support value queries. Okay, and then maybe to make this a bit more concrete and also connect back to the hiring marketing expert problem, and kind of reflecting also similar assumptions in like revenue maximizing auctions. So maybe a very natural starting point would be that the outcome space you can think of as being items that are included in an outcome. And maybe items is not the right word here, but maybe you want to say basic events, that a certain visitor was attracted or not. So this will be like our outcome set will be 2 to the m, so it's exponentially sized. An outcome will be a set. And there are little m many basic events that can occur. Okay, but the outcome space is 2 to the m, so it's exponentially large. And then maybe a natural assumption also is that if you take an action, then there's a product distribution over possible outcomes. So whether a certain visitor comes or not is basically an independent coin flip QIJ. So what you do, agent takes action I. For each outcome for each item or basic event that can happen. You flip a coin with probability Qij and include it into the outcome S or not. Okay, and then there's an additive reward function, which just associates a certain reward to each basic outcome, and your reward will just be the sum of realized items. Okay, and then what we want to do in this case is we want to find an optimal contract. So as before, a mapping from outcomes to non-negative transfers. So a succinct Pauli representation of that. In time, that's polynomial in the number of actions n and in the number of items m. Notice that this is logarithmic in the outcome space. Okay, and in this concrete setting here, just from LP consideration, it follows that there is such a succinct description. Okay, so how can we find it? Okay, so let's maybe make this picture that Inbal was alluding to earlier a bit more concrete. So this is like how this could look like on paper, right? So this is the marketing expert example. So in this case, the marketing expert can put in 3 levels of effort: no effort or low effort, medium effort, high effort. This has cost C1 being 0, 1, and 2, so higher effort, higher cost. And then we have possible outcomes, so either no visitor comes, a general visitor comes, a targeted visitor comes, or both visitors come. Notice this set structure here, right? So it's either one or the other or both. And I've set it up here in a way that the rewards are indeed additive, and the distributions here are product distributions. Of course, maybe in your real-life application, that's a bit of a simplification that it's actually independent, but often, I mean, see in auctions, this is kind of a good first step to understand the problem. Okay, so this is succinct. Can we compute the optimal contract? And now also, like, leveraging what you saw in the first part, there you saw this like min-pay LP, right? So one approach for solving this problem would be look at your n actions, so there are only polynomially many. For each of these actions, find kind of the minimum transfer that you would have to make to incentivize it, take the best one. Okay, so the problem, of course, here is that this will no longer be a poly-size LP that you want to solve. Okay, so let me make this a bit more concrete. Right, so we have an action AI. We want to find the minimum transfer that implements action AI. So using Inbal's notation, so we would have this FIS, which is the probability of outcome S under action I, right? And it's just using that it's a product distribution. And then the LP would look something like this, so minimize the transfer, so it's the expected payment, subject to, and that's kind of the agent, payment to the agent, minus cost, so that's the utility for action I, versus any other action I prime. So it's just saying agent I should choose to prefer action I over any other action. Okay, and the problem, of course, here is that we now have exponentially many variables. Right? So this would just yield an exponential time algorithm. On the other hand, we only have few constraints, right? So we just have constraints for action, so n-1. So we could think that maybe we can switch to the dual and use ellipsoid. And in fact, doing this, I mean, this is what we do, but it turns out not to be obvious, and it's also not leading directly to a good algorithm. Okay, so indeed, if you write down the dual, you will have these dual variables, lambda I prime, n-1 many, right, for each constraint. So the objective is something related to costs. Interestingly, we'll have these constraints here, right? So fixing the dual variables, so the left-hand side here is just a constant, and on the other side you have something very interesting, so that's in the box here. So that's for all S, you try to find something for set S, and what is it? Right, so at the top, you have something like a mixture distribution, right? So you weigh the different distributions for different actions I prime with lambda I prime. I mean, it's not normalized, but you could make it such. And for some action S, and you compare this to the probability of that set under action I. Right? And so since this has to hold for all S, I mean, you could basically just find the minimum here to see if there's a violated constraint. Right? So that's for the separation oracle. And now I think this is where this computational approach for the first time really highlights structure. Right? So what are we doing here? Right? So we are trying to find something that's related to the minimum likelihood. Right? So we try to find a set S that in this mixture distribution is comparably more likely than in the original distribution is. So it's a good predictor in some sense. Okay, so that I found interesting. And the other thing that I found interesting is that if you picture this, kind of this box which I had, like the principal agent matrix with the probabilities, then what is this doing? So it's basically mixing over actions, and you're trying to find a set S with relatively low probability there. Okay, and now what makes this a hard problem? I mean, you saw the bullet here. So what makes this a hard problem is that if you start from a product distribution and mix it, then it ceases to be a product distribution, so it becomes correlated for 3 or more. And this is kind of intuitively what makes the separation oracle hard. And indeed, you can show that this separation oracle is hard even for constant n at least 3. Not only is the separation oracle hard, but also the problem itself is hard. So what do we do? And let me, in one slide, highlight a result that we have. So that's kind of a positive result, which I quite like. So it's saying that there is an ellipsoid-based algorithm that for such a succinct setting, so we have like outcome spaces sets with m basic elements and a parameter delta, we can find a delta IC contract, so a contract that's not exactly IC but approximately so, that gives payoff at least opt in time polynomial in m at 1 over delta. And intuitively, how do we achieve this? So the basic idea is that, I mean, I showed you this dual, and that separating it is hard. But what you can do is you can solve it approximately. So in fact, there's an F Peters for the separation oracle. Now there are standard techniques for lifting this into approximation results. However, they often rely on some kind of scale freeness property, which this problem doesn't have. So we cannot use these kind of standard techniques. Okay, so that's basically how we get there. We are relaxing the constraints, so this brings us to delta IC. I think that's also like an independent nice contribution here, because like delta IC was very influential and important for algorithmic mechanism design. Okay, so all of this is polynomial in M, like the basic outcomes, so logarithmic in the outcome space, and 1 over delta. It's not polynomial in N, so this is only for constantly many actions. And in fact, we have this sharp dichotomy in the paper that if you go to general n, then this problem becomes crazily hard. So it turns out to be hard to approximate within any factor with exact IC, and even for delta IC, delta being sufficiently small. Okay, so let me quickly wrap up this direction. So I think that's just one of many conceivable succinct formulations which explore rich outcome spaces. What I particularly like, it's kind of a positive result despite this rich outcome and for the optimal contract. It's not just for linear contracts. And yeah, as I said, I'm hoping to convey this idea that like the computational lens puts a spotlight on structure, and here's one such example, right? So it's putting this inference in the spotlight. All right, so let me switch to a different perspective. So now I want to look at combinatorial contracts, but now with many actions. Okay, so the basic situation, so you're writing your PhD thesis, you can do different things, you can submit your paper there or there, you can go to the conference, talk to this person or not, right? So it's kind of a rich set of things that you can do, and it seems natural to assume some kind of diminishing marginal returns for the more things you do. So how can we use this? Okay, and that's the model from a very recent paper with also Michal and Thomas, both in the audience, so with Ezra, Feldman, and Kesselheim. And as before, I want to take or keep some of the problems aspects simple, and others I want to make combinatorial to really isolate the effect. Okay, so in this case, the thing that I want to blow up is the actions. So I want to assume that there are n basic actions that you can take, like talk to someone, submit your paper to STOC or to Fox. And then the agent takes a set of actions. So S subset equal A. Each action will have a cost, C of A, non-negative, and I will just assume that costs are additive. And then there's kind of a reward function or a success probability function that takes a set of actions and in this case maps it to success or not, like 1 or 0. So it's mapping from 2 to the A to 0, 1. And I will assume that we have a value oracle to this. So if I plug in a S, it gives me a value. Okay, And kind of where kind of this diminishing returns now will come in is through this f. Right? So this is like living on this set, right, and maps to a number. And I want you to think of f coming from this hierarchy of valuations with diminishing returns. So you most likely know submodular, right, where you take some set, you add something to a set, and if you add it to a smaller set, then the marginal contribution is larger than when you add it to a larger set. But in fact, there's of course a rich hierarchy of such valuations. In particular, in economics, one that plays a particular role is gross substitutes, which is for you, I mean, at the moment you just need to know is like a strict subclass of submodular. Okay, and then what do I want to do? So it turns out that in this case, when the outcome is binary, designing an optimal contract is actually tantamount to designing a linear contract, as you saw in the first half. So it's just setting a scalar that maximizes the principal reward. So the principal will now post this alpha. The agent will choose a set of actions S. An outcome will be realized. So this is f of s. And then the agent will be paid alpha f of s. And the principal will retain 1 minus alpha f of s. Okay, and all of this is kind of a game, right? So it's always subject to the agent actually choosing s. Okay, so what can we do here? And I think there's a very nice geometric intuition for what's going on here. And that's building on kind of an upper envelope diagram that I first saw in our own paper with Inbal and Tim. So what do we do? So I'm looking here at the agent's perspective. On the x-axis, I just have the contract, right? So recall this is just a scalar between 0 and 1, alpha. And I'm plotting the utility that the agent gets from choosing certain sets of actions. Okay, and in this case here, importantly, down here, so I've set it up such that the f function is actually additive. Right, so it's 0.3 for outcome 1, 0.2 for 2, 0.5 for 3, and then it's just the sum. Okay, so it's an unrealistic special case. I mean, just for the purpose of illustration, costs are additive, right? So then what happens here, I mean, you can take all the possible subsets of 1 to 3 and plot the agent's utility for a given set, right? So for a given set, right, so it's f of s is fixed, and it's just multiplied with alpha. So it's just a linear function with slope f of s. Okay, so that's what I'm doing here. There are eight many, and from the agent's perspective, I mean, recall she is trying to maximize her utility. So she's trying to maximize alpha s. So she's basically looking at this upper envelope, right? So trying to pick a set that's best here. And in this case here, this makes her life very easy. So depending on the alpha that the principal chooses, she can just look up the upper envelope, and she will take the set that maximizes her utility. And also notice that while there were like many possible sets that can be chosen, actually this upper envelope here turns out to be polynomial in size, at least for additive f, right? So it's, in fact, even easier. It starts empty, then it adds 1, then it adds 2, and then it adds 3, right? So it's just adding items 1 by 1. So linear size, okay? Now from the principal's perspective, so notice that I'm changing here from the agent to the principal. So that's the principal utility. It's 1 minus alpha f of s. So it also depends on the agent's best responses. So that's why I kept kind of this subdivision into sets chosen. But now the principal utility is like 1 minus alpha f of s. So it's kind of in a region where the agent's choice is fixed, it's actually declining. Right? So from the principal's perspective, only kind of the leftmost points are interesting. Right? So that's the alphas that you would choose. And also notice that even for additive, this function is a bit nasty, right? So it's not continuous, it's jumping, right? And it's maybe not even guaranteed that it's a convex function. Okay, so that's kind of the mental picture that I want you to have in your mind. Okay, so what did we do in that paper? So we identified kind of these interesting alphas, and we gave them a name. So we called them critical alphas. And CFC is our notation, so critical for reward and cost F and C. So that's the set of critical alphas. And a simple observation is that since optimal contracts are linear, one of the critical alphas will correspond to your optimal choice. Okay? So in principle, here's a potential algorithm that you could use, like the naive algorithm if you want. I mean, next to naive. Right? So you could just maybe try out all possible critical alphas. Okay? Next to naive, I mean, it requires two things, right? So one is that you have some subroutine for going over all alphas, so some iteration that you can do. And you need a bound on the number of critical alphas, right? So I showed you the example with additive, and that turned out to be nice, like it's a polynomial number of interesting sets of action on the surface, on the envelope. But of course, with richer F, that's maybe not guaranteed. And in fact, that's not the case. Okay, so here's our main result that I want to highlight. So it's from our Fox paper. So what we showed there is that for gross substitute valuations, actually this first algorithm that comes to mind after having this picture actually can be turned into a polynomial time algorithm that finds the optimal contract exactly. Okay, and it's basically relying on two things. So one, I would say, is the easier part. So it's using properties of gross substitutes. For example, that the greedy algorithm can be used to find a demand set and things like that. So known results. And a new result, which is bounding the size of this critical set. Okay, and then on the other hand, we show that for submodular valuations, it's NP-hard. And even more so, there are submodular functions, so in fact only coverage functions, for which if you draw this upper envelope diagram, actually every possible subset of actions appears on the upper envelope. So exponentially many. So this also rules out this approach. Okay. And yeah, so again, like my high-level agenda for this talk was kind of pinpoint nice connections. And I think here's another very nice one. So if you, in this problem, take the perspective of the agent, right? So the contract is fixed, alpha. Now what does the agent try to do? So he tries to find a set S that maximizes her utility, right? So she's paid alpha times f of S minus the cost. Okay, and then, I mean, very simple algebraic manipulation. So you just divide by alpha. Then this is looking like f of S minus 1 over alpha C of S. Right, and recall that in our model, we took costs, and I think that's also a very natural assumption to be additive. Okay, so what this should remind you of, at least if you've worked on auctions, is that this is just a demand query at item prices CA over alpha. Right, so that's your valuation function, a gross substitute submodular function, and these are item prices. So the agent is trying to find a demand set. Okay, so this is just a demand query in auctions, which I already found a surprising connection to pop up here. Moreover, this is really kind of the intuition and mental picture that we are exploiting for the positive result. Right, so what do we, with this mindset, what do we need to achieve? So we somehow want to bound the size of the demand relation, like how many sets can be on this, in this demand relation. And it turns out that the non-standard thing here is that what we need to think about, thinking of F being gross substitutes, is that we have item prices, but now we move them in lockstep. Right? So we change them at a rate of 1 over alpha, all of them simultaneously. We want to try to understand how the demand relation changes. And what we show is that then only simple things can happen. So either an item enters as an additive, or you have one-to-one substitutions for cheaper items and more expensive items. And this enables a potential argument giving a polynomial bound. And as we saw for submodular, this doesn't work. So very nice connection to demand queries. And as I said, more high level, I also found it nice that kind of this gross substitutes being the frontier of tractability turns out to be true again, this time for contracts and not for auctions. More generally, I like this connection to auctions, right, which comes through this demand perspective. And think about it, I mean, it actually only motivates thinking about demand queries at all in this context. I think there are a number of additional results that we have in the paper. So we have an F-Peters for general F. Coming back to what Inbal did in the first half, we also have like a robust optimality result for linear contracts in this setting. So with non-binary outcomes, linear contracts turn out to be maximum and optimal, and then all our positive computational results translate to optimal linear contracts. I think there are some very nice open questions here. I mean, motivated by this connection, for example, to demand queries. So for example, for submodular valuations where kind of this set of critical alphas, this orbit can be exponential size, can we use, for example, demand queries to get a good approximation. Okay, now let me change gears for the last time. So in this final part, I want to again talk about combinatorial contracts, just to hammer this down, but this time with many agents. Okay, so the like motivating example here would again be you're running a team, right? So you're a manager, and you try to incentivize your team to do the best they can. And as before, I should say, sorry, that this is really not my model. So it's from this pioneering, very nice work by Babayev, Feldman, and Nissan from already 2006. And what I wanted to say is that as before, I will keep some aspects of the problem simple, and I will make others combinatorial to highlight kind of their role. So in this case, there will be n agents. So I have red, blue, and green here. And now I'm trying to incentivize agents to either take effort or not. So there will just be a binary action, right? So I include an agent or not. So that's why I put the circles here. Agents will have a cost for effort, no cost for not doing anything. And I will also keep a binary outcome. So either my project succeeds or not. Okay, now I'm trying to identify the set of agents to effortize, so to induce them to exert effort at cost, so that I maximize my revenue. So success minus what I transfer. Okay, and again, similar to the previous problem, I will have this function f, which maps kind of activated agents to success. Okay, and again, I think it's natural to assume some sort of diminishing returns here. Okay, I mean, lots of math here, but actually simple. So actually what I only want to say is that also in this case, binary outcome, it will turn out that linear contracts are again optimal. So that makes it very nice and easy to think about it. So we just want to find an alpha I for each agent. And alpha I fs will be what I transfer to agent I. Right, so it's now n-dimensional, but otherwise it's the same. And then a bit of notation. So if S is my set of agents that exert effort, then I have this notion of marginal effort, which is how much does F increase if I add agent I to S, right? So that's Fi given S without I. It's just F of S minus F of S without I. So how much F increases by adding I. And then it's very easy, right? Because it's binary action. So we want to understand incentives, we just need to understand does an agent want to exert effort or not? Okay, and that's what the agent would get if he exerts effort. So it's alpha I times Fs minus Ci, and she compares this to not doing effort, so no cost, but then also F is lower because she doesn't contribute to it. Okay, and then from this, it's clear that kind of the interesting alphas are clear, right? So you want to find the smallest alpha that satisfies this inequality. This turns out to be this. So it's just cost divided by marginal, which also has a very nice economic meaning. Okay, but still the principal problem turns out to be non-trivial, right? So what are we doing here? So we're trying to maximize this G of S function, right? So the principal wants to identify the set of agents to incentivize, and what the principal gets is like F of S times 1 minus the sum of the alpha I, right? And I've substituted the alpha I here. And notice that even when you start with a very nice function, say F is submodular, then, I mean, this G here loses almost all of these properties, right? So it's not necessarily non-negative, it may be non-monotone, it's probably not submodular. So can we hope to do anything? And to make this point a bit more concrete, I want you to think of one particular submodular function F, a coverage function. Okay, so very easy. So it's a subclass of submodular. So we have the agents here on the left. Each agent can cover certain tasks. So, for example, blue can do 1 and 2. And then my value for a set of agents is just how many tasks they can cover. Okay, so for example, for red, this will be 2, because you can do the first and the last thing. For red and blue, we actually get 3 things covered. So that's my F. It's a submodular function. And I also can think about like marginal contributions. For example, if you look at red given green, so green already does 3 things, one of which is also covered by red, but red contributes 1 new thing. So the marginal contribution of red is just 1. Okay, so that's nice. So let's revisit the principal objective with this in mind. Right, so it's g of s, f of s, 1 minus the alpha I, so s without I wrote as s minus I here. So then this f of s is nice, so it's just the total number of items covered. Right, so it's just maximizing a monotone submodular function. Right, we all know we can do this, or at least get a constant approximation to this. But then we have this nasty 1 minus thing here, so what is this? And I think one interesting intuition here is that somehow we want to make the sum of the alpha i's small. So in some sense, we want to choose agents with small cost, but maybe they all have the same cost. But then we want to make their marginal contribution large. And what's the marginal contribution of an agent? So that's really just the items covered uniquely by an agent. Okay, so that's kind of the 2 forces here. Covering, but not so many overlaps. Okay, and it turns out that unique coverage, and it's a very nice Soda paper from 2006 by Dimain, Feiger, Hajagai, and Salavatipur. Unique coverage is actually hard to approximate. So there's semi-logarithmic hardness for approximating this. I mean, this doesn't mean that our problem is hard, but it sort of says that, like, intuitively, we're somewhere between the two. So, like, this tractable coverage optimization, and on the other hand, we need to take care of this. Okay, just as a quick advertisement, so it's unpublished. So an ongoing work also with Thomas Ezra, Michael Feldman, and Thomas Kesselheim, we managed to show that there's actually a polytime algorithm for submodular f that gives a constant factor approximation for submodular f, as I said, using only varioarical access to f. Okay, and somehow, like, what turned out to be tricky here is that neither of the obvious benchmarks works. So if you just take f as a benchmark, so your number of items that you cover in the coverage case, then that can be too far apart and too much to hope for the objective, because the 1 minus part really pulls it down. On the other hand, just maximizing for unique coverage can be a bad idea, because this f can be just very big, and then the unique coverage is somehow disconnected from this. Okay, and how do we show this? I think we have this very nice novel relaxation here of opt that somehow uses that. Here in this case, when we have multiple agents, it's really an equilibrium problem, right? So this f of s, I mean, it lives on s and depends on what the other agents do, right? So like agent I is best responding almost as in a Nash equilibrium. And what we do is that we show that if you take these local optimality criteria that have to be satisfied by this optimal solution and relax them a bit, then this gives you a nice thing to target. So it's within a constant of optimal, but can also be well approximated. Right? And it's not that we can approximate that problem, we just need to guess the value of that solution, because then what we will do, and I think that's also very nice, and I still have to understand what's actually going on a bit. So we have this relaxation, and then what we do is that we'll actually derive item prices on agents for these relaxation. We post these items prices. We, at least conceptually, run a demand query. I mean, of course, for submodular we can't, but we can do something approximate to identify a set of agents, and then we incentivize them optimally using these alpha i's that I wrote down, like the optimal alpha i's. And this turns out to be a constant approximation. And here I like the connection to prices. Okay, and more generally, for f sub additive, we can show that you may need to issue exponentially many value queries to get even a square root n approximation. Okay, so there's been prior work which looked at it differently. I will just put it up briefly, not go into detail here. Yeah, I think what's very nice, it's kind of what I would say kind of the first real approximation, real constant factor approximation in this wider context. I mean, further connection to optimal combinatorial optimization, like submodular evaluations, coverage, and other problems. I find this technique exciting, which goes through item prices, which maybe at first sight is not the right thing to do. And there are many nice open questions, so beyond binary action, which is something we work on, and also like following up on Michael's early work, there are some questions that are still open, even though this is now 14, 16 years old. Yeah, very briefly conclusion. So I hope that I could convince you that this complexity approximation lens is interesting and sheds new light on contracts, just as we did with auctions. And there are many open problems to explore, and I hope to see some of you solve them. Thanks.
Thank you very much, Paul. I think we are kind of out of time, so let's take the questions offline. We have a break now, and we are returning at 1:45? Yeah, okay, for the next tutorial. Thank you all. And let's thank both speakers again.